Hey guys, welcome to another chapter. My name is Cesar Hernandez, and I'll be talking about a brief summary on attention mechanisms and storage in a transformer and the roles in artificial intelligence. So we're going to look over the introduction, attention mechanism, storage, and its conclusion. First of all, we're going to talk about attention mechanism. What does it do? How does it work? Why does it work? So we're going to explore the attention mechanism in transformers, which are a key technology in AI and large language models. It explains how attention processes data, refines word meanings through context, and utilizes multi-headed attentions to enhance its understanding. The basics of attention mechanisms. So attention mechanism is based on how humans selectively focus on certain parts of information while processing data. So the attention mechanism is a technique in neural networks which allows the models to focus on important parts of the input while processing data. It is widely used in natural language processing, NLP, such as computer visions and other AI applications as well. Why is attention needed? So traditional neural networks, like recurrent neural networks, process information sequentially, meaning they struggle with long-range dependencies. We could see attention helps models to focus on relevant parts of input data, how to handle long sequences efficiently, and how to improve contextual understanding in tasks like translation, summarization, and image recognition. Components of attention, there are three vectors specifically. The first one will be the query, the key, and the value. First of all, the query vector. So each word generates a query vector that seeks to identify relevant words in the context. Next is the keys. So every word also produces the key vector that can respond to queries, and the value, which represents information that will be passed to other words based on relevance determined by the queries and keys. So going back to the query, so each word has a query, which means it has its own address or specific value generated by the word. The key is tied to the query in form of selecting the next key that matches the next query, if that makes sense. So for example, brown is associated to the key value of one, and creature, for example, is associated to the key value of two, key vector of two. So hand in hand, they work together by associating the relevance of each query and the key. So how attention works, once again, so it computes the attention score, it applies the softmax, it adjusts the weights and values, and returns the sum of the results. Masking intention. So during its training, it is crucial to prevent later words from influencing earlier ones, and it is achieved through a process called masking, which implies that the data or the tokens that are set to a negative infinity before applying the softmax function, which ensures that the columns remain normalized while preventing information leakage. So that just means that due to the softmax, it'll allow later in the future, when running the transformer or the large language model, it won't affect later words. For example, if you see the word mole and mole in the future with two different connotations. Updating the embedding. So once the attention pattern is established, the model updates the embedding based on values associated with the relevant keys. For example, if the word large is relevant to creature, the model will adjust the embeddings of creature to reflect a more specific meaning, such as a large blue creature. I would now like to talk about the different attention types. There are three, four attention types, such as the self-attention, where each word in the sequence attends to every other word. It's used in transformers like BERT and GPT. There's also soft versus hard attention. In soft, it assigns a weight to all elements differentiable used in the most AI models. And then there's hard attention, which selects a few elements with discrete choices that are non-differentiable used in reinforcement learning. And then there's also multi-hit attention, which uses multiple attention heads to capture different types of relationships in parallel. However, in our transformers, we use multi-headed attention where multiple attention heads operate in parallel, and then each head has its own distinct key, query, and value matrices, which allow the model to learn various ways that the context can influence meaning. In the example of GPT-3, which employs 96 attention heads, each contributing to the overall understanding of the text. And the learning outcome of this is that the attention mechanism is the cornerstone of transformer architecture, which enables models to process and understand language in a nuanced way by allowing the words to influence each other based on context. Next, let's talk about remembering facts. How does a large language model remember facts? So, a large language model have become a significant topic of discussion in the field of AI. One of the aspects is how they store factual knowledge. We will see how large language models store factual knowledge, focusing on the role of multi-layer perceptrons, MLPs, for encoding information through high-dimensional vectors and matrices operations. The role of the multi-layer perceptrons is that recent research from Google DeepMind investigates where factual knowledge is stored in LLMs. So apparently it's stored in the perceptron layer, and the researchers have concluded that the factual knowledge appears to reside in the specific part of the neural network, which is the MLP. How MLP processes information. So the computation within the MLPs is straightforward and is comparable to the intention mechanism. It primarily involves the matrix multiplication and nonlinear activation functions. So to better demonstrate this, think about it this way: the MLP can store a specific fact, such as Michael Jordan plays basketball, and we could break down the process into steps. So the multi-layer perceptron operation goes as follows. The matrix application multiplication, which is the learn parameter probe feature, nonlinear activation, which filters irrelevant information, and the output updates original vectors with refined information. The role of nonlinear linearity, the nonlinear activation function, is crucial because it allows the model to differentiate between various inputs effectively. Why it matters? It helps differentiate the meanings between two tokens or words, for example. And the example is if an input vector aligns with Michael Jordan, the MLP operation may reinforce the connection with basketball. So it associates the person to an object depending on their context. The concept, the concept of superposition is how superposition stores facts. So superposition is a single neuron could be a single neuron which may encode multiple overlapping features. In a high-dimensional space, nearly perpendicular directions store diverse information. So high-dimensional space being bigger than the 4D, 3D, if anything, which in every direction there's a single vector which has information correlating to the next word or previous word. The implications on interpretability. So is the idea that superposition complicates the interpretability of LLMs. Instead of a single neuron lining up to indicate a specific feature, a combination of neurons may be activated, which is representing the superimposed feature. And the phenomenon highlights the challenges in understanding how LLM encodes and retrieves information. The learning outcome is that large language models such as GPT-3 utilize multi-layer perceptrons to store and process factual knowledge through high-dimensional vectors and matrix operations. Next, I'd like to talk about the softmax function questions, which are why or how softmax converts a list of numbers to a list that sums to one. And the next question is how or why does softmax keep the relative order of numbers the same, but stretches out the larger numbers to make them significantly bigger than others? So to answer those two questions, for the first one is first softmax function applies the exponential function to each of the numbers in the list. Then it uses normalization in the end, which divides each exponential value by the sum of all the exponentiated values in that list. And for the following question, softmax keeps its relative order through exponential differences, which means that the difference between the large and smaller numbers are magnified. And then next, softmax as well uses normalization to maintain proportions, which ensure that the larger numbers that are disproportionated will stand out while still preserving their original rank. And as for the code, on the left-hand side, we have the original code, and on the right-hand side, we have the modified code. And we can see a difference in the values that are being outputted in the modified version. It climbs rapidly compared to the original code. And I'd like to talk about the significance of the modified version. In the modified version of the code, the differences are of the growth behavior, the effects on the probability distribution, and the impact on the application.